The Colloquium committee likes to think that we only have good colloquia, but it's a very rare occasion when I'm able to introduce someone as prestigious as our speaker today. Helen Quinn is a co-author of two of the most important theoretical papers in particle physics in the second half of the 20th century. This is, the first is on the unification of coupling constants. The second is on the famous Pache-Quinn solution of the strong CP problem, which led to the invention of axions, which might be a candidate for dark matter. I think it's fair to say that in this department, the particle theorists, each and every one of us, have spent a fair fraction of our own time just doing follow-up to those two papers. So Helen was recently awarded the Sakurai Prize for her work in the American Physical Society. And she went on after that. She made many contributions to the study of CP violation in connection with the Bavard detector at SLAC. And then she wrote a mystery story. Okay, this is a book, I don't know how many of you have read it. It's a really remarkable book that Helen and Yossi Meir wrote about the question of why there's more matter than antimatter in the universe. And it pulls together all kinds of threads of particle physics into a unified whole based on just that idea. It's a really wonderful book. I encourage you to all go out and buy it. Helen is, has devoted a considerable amount of time through that popular book and other things to outreach. Here's an example. Here's the standard model on a placemat that you can get for your kitchen. This is not Helen's original version, which was a lot prettier than this, in my opinion, but it's the updated version that the Particle Data Group created based on Helen's original ideas. I think that what Helen has been doing lately might turn out to be more important than even the great scientific work that she's done. She's been the chair of the National Academy panel on science standards for K through 12 education. And all of us got here because of some good science teachers and good science teaching in K through 12 education. And it's really important that we continue to update the standards, and Helen has been, I think, the person behind this effort in the National Academy, and has really made major contributions, which she'll tell us about today.
Thank you, Tom, for that overly generous introduction. So what I'm talking about is actually an effort of many, many people. My role is, I am the chair of something called the Board on Science Education. In the National Academy, there's a Board on Physics and Astronomy that does studies about the future of physics and astronomy, and there's one on science education. And we were asked, actually, by the Carnegie Corporation of New York to start the process of developing a next generation of science standards. And I took that on and was chair of the committee that developed the first stage of this. So I'll explain the stages in just a minute. The first stage is called the Science Framework. That's where I really put my work. The standards then follow from the framework in a very direct line. Education is a state issue. And if the federal government tries to tell the states what the curriculum or what the standards should be, the states react very negatively to that. States develop state standards as a way of defining, because each teacher actually defines the curriculum in their classroom. So having something that said, okay, when you teach 5th grade, you teach something particular in 5th grade, at the state level was revolutionary back then. We've come away since then, and there's something called Common Core for math and for language arts. 47 states have signed on to teach the same thing in 5th grade, to have common standards. I mean, why is math different in Texas and in California? Well, only because Texas didn't sign on to this. The idea of having common standards has a lot of weight because it means everybody who's working on developing curriculum materials is now working in the same direction. And you don't have to have a book that's this thick because it has to cover everything every state wants to do. It can be this thick and cover what's actually being covered in that grade level. So this is a helpful, and maybe you can move education constructively by having this common view. So then the Carnegie Corporation thought, well, you should do this for science too. So they funded the process, and in there was 2 stages. When you start out to write standards, what should every student learn? You're down in the weeds. You're looking at the bits and pieces of knowledge that you want everybody to achieve. Let's start first with the big picture. What is it you want everybody to know about science in a general way? Not writing it in terms of things that can be measured of do they know this or not. And so we had the privilege of writing the framework, which is to define what we think is important in science learning, and I'll tell you a lot about what's in that framework. The second stage, there's a nonprofit organization called Achieve, and they put out a request for states to make a bid to be part of the process of developing a common set of state standards. Thinking about what goes on in the classroom, of course, neither a framework nor standards is what happens in the classroom. What happens in the classroom depends on the curriculum materials, on the teacher's instructional choices, on the professional development that teacher has had both before they became a teacher and while they're in service, and on what is tested. Particularly today, when a lot of teacher evaluations are based on student scores. But anyway, if there's a test that's testing what students in a certain grade should be learning, teachers are going to teach to that test. So we'd better make that test be testing what we really want students to learn. So changing assessments is part of the forward agenda of this process. Changing how we measure and evaluate student learning in science. The task of the framework was just to say, for every student in K-12, not just the students who are going to be physics majors in college, not just the students who already want to go on in science, but what should everybody know? What does every citizen need to know? What kind of background in science is important for every student? And we thought not just knowledge, but also more than knowledge, and I'll talk about what that more is. The committee itself had 9 scientists, 2 of them Academy members, 2 of them Nobel Prize winners, and 9 people with expertise in science education, a variety, like people who'd been the state science supervisor, people who did research on learning in science, people who had been a kindergarten teacher and now ran a program preparing early childhood teachers. So all different levels of expertise in science education represented on this committee. We decided to just define science in 3 dimensions. Now normally when you think about what should students learn in science, it's all in that 3rd dimension of the disciplinary core ideas. What are the ideas you want students to learn? But we say no, that's the 3rd thing, and besides we'll come back to the word core because that's important too. To great an extent today, for most students going through K-12 education, science is a sequence of disconnected facts. There's no way of connecting what they're learning in their biology course to what they're learning in their physics course. And in elementary school, it's just whatever interesting activities or facts that teacher thinks would be good to teach them. So it's a little bit of a mess. And we said, no, we really want it to be coherent and connected. And first we want to start with what scientists do. Science and engineering practice. And that for 2 reasons. One, because unless you know how scientific knowledge is arrived at, how can you differentiate astronomy from astrology? You're just being told this is so, then you know nothing about science. So understanding how scientists arrive at the knowledge that they express as scientific knowledge is very important. But also, as a student, how you arrive at understanding the concepts of science is you have to go through a process yourself of developing your own concepts. And when you'll see the practices, you'll see that one of the goals of engaging students in these practices is to get them doing the active thinking work that has to happen in order to go from a naive conception to a more scientific conception of the subject, in order to learn rather than to layer a new set of facts on top of the one they've known before and not really make the connections. Secondly, and for some of the same reasons, cross-cutting concepts. These are the big ideas of science that usually we just forget to teach. We leave them as something you're supposed to get, that like science is about cause and effect. Science is about modeling systems and interpreting the behavior and phenomena within the system. Or, and you'll see the list in just a moment. And then finally, in each of those areas, what are the core things that students should learn and develop their understanding of over multiple years of school? Not everything in the discipline, but just certain central ideas that are going to be important and build a base on which future science learning can happen. And by defining science as having these three dimensions, we didn't mean we should teach them separately. We should teach your list of science practices, you should learn what they are and be able to recite them. That's not what we meant. We meant students should engage in the practices as a way of learning the disciplinary content. What are the practices of science? Here's the list. I haven't found any scientists that argues with this list. And it's science and engineering. But the interesting thing is, we only have to differentiate science and engineering for two of the practices. The one that starts the process. In science, you start with some kind of question. Of course, you don't actually start with a question. That's one of the problems, right? You have to go around in cycles here. You start with some exploration of some phenomenon you don't understand, and that generates some questions. And then the questions lead you into a process of investigation. And that process involves developing a model, because models are what scientists use to describe systems and to think with. Planning and carrying out investigations, analyzing and interpreting data, separated, because there's an awful lot of school science where your students do hands-on investigation of something, but they never analyze anything. Using mathematics and computational thinking, developing explanations, that's the science, that's the end of asking questions, and designing solutions. So the defining problem is the engineering term. When you start an engineering exercise and you're going to design something, before you really start designing, you have to define the constraints on your design. You have to define what problem you're trying to solve and under what conditions you're trying to solve it. And designing solutions is the process of doing the design. Today, in the world of online information, memorizing is a waste of time. You do memorize when you use something frequently, and that's valuable because it speeds up the process. But just memorizing in order to memorize, that's silly. What you need to do is be able to decide, because you can get the information on the web. However, you can also get a lot of misinformation on the web. So how do you figure out what's the good and what's the bad on the web? Well, you need some criteria for thinking about that for any particular problem. And evaluating the information is as important as obtaining it. And then when you're doing all these other practices, it's not very useful unless you can communicate what you're doing to somebody else. So communicating is also a skill scientists need. So this is our list of practices. The ones in red are the ones that I think are kind of missing in most science classrooms. And you notice it's most of the list. So this is a problem. Physics classrooms have some using mathematics. They have very little computational thinking. It is a skill one needs to develop in order to, for example, analyze and interpret data. Patterns is one, for example, where in many, many situations in science, what you do is notice a pattern and then try and figure out what's the explanation, what's the mechanism that's generating that pattern. Or just noticing a pattern in order to do classification, which is the first step of understanding things in the life sciences. Classification is a very much bigger thing than it is in physics. It's an issue in astronomy too. So figuring out how to devise useful ways of classifying starts with noticing that there are some patterns here, and they need to be explained. Cause and effect is pretty obvious, but the notion that cause and effect needs a mechanism, that's important. Scale, proportion, and quantity. Whatever problem, whatever system you're thinking about, in order to say, what am I doing with this, how am I going to model this system, I have to decide on what scale I want to model it. Let's think about a bicycle. If I want to explain how you ride a bicycle and how it works, of course I'm going to model it on the scale of pedals and cogs and wheels and chains. However, if I want to build a better bicycle, and I want to find the best, lightest, strongest material to build my bicycle of, I have to start thinking about modeling materials at the atomic scale to do material science and get better materials for better, lighter bicycles. So depends what question you're asking about the bicycle, what scale we have to be thinking. The same is true if you're talking about the human body or an ecosystem or Earth and Earth system science if you're trying to talk about climate change. Yes, you have to model things on the scale of the whole Earth, and you also have to model chemical process at the atomic and or light and the different wavelengths of light and how they interact with the atmosphere. So clearly, thinking about scale, but also thinking about proportion and quantity and number is clearly part of what we have to do to really explain things in science. I've talked about systems, I've talked about modeling. Actually, it's very convenient to have a set of 5 or 6 questions that you can ask for anything you're studying in science. Right? What system are we looking at here? What are its components? How do they interact with one another? What's the boundary? What's flowing in and out of the system across that boundary? All of those things help clarify thinking and help make models more explicit and specific. And having those repeated questions that you use in biology and you use in chemistry and you use in physics begins to show you why those subjects are connected. Because they really are using some of the same thinking patterns. Energy flows, energy conservation, some people said that should be one of the physics concepts. We put it here at the level of cross-cutting concept. The conservation of energy and matter applies on any scale of system, and it's very important to understanding the way those systems are working, whether we're talking about the climate or the human body or a physical system in the laboratory. One of the big struggles in working on the framework, trying to make the understanding of energy flow in some kind of rational fashion as you develop the disciplines. I gave one example at lunchtime today. I mean, there's no point in talking about we get our energy from respiration if you don't understand a chemical process where energy is released when sugars interact with oxygen. So how do you coordinate the learning in biology, which even in very young kids you can say, oh, organisms on the surface of the earth need to breathe and they need to eat in order to live, up to understanding energy in biological systems. And so figuring out how these things phase together across the disciplines, which learning comes in which order and how to get it together, that's one of the things we had to work with, to put together a coherent framework for this learning. But the language of energy is different in different disciplines. We can't fix that at the level of K-12 education, but we can help students understand those differences and the fact that really it's the same concept of energy we're talking about. We're just focusing on different parts of it when we're doing physics and we're doing chemistry and we're doing biology. Because those connections are not going to be made unless the instruction helps students make them. At least not by most students. So the list goes on down. It's funny, there's an 8, but there are only 7 of them. The 8 is simply there because I put the line that said, all of these cross-cutting concepts require us to think in terms of models to make those connections across. And modeling is very much left out in the current curriculum. So this whole idea that modeling is a key skill for science learning is, again, it's left implicit, and we think it should be made more explicit. So now here is a summary of the core ideas of the disciplines. It's kind of amazing you can put it on one page, right? Of course, they're big ideas. Matter and its interactions, well, that's all of chemistry and quite a bit of physics, right? Motion and stability, every physics student recognizes that one. Energy. Number 4 under physical science is a little strange. Number 4, we took sound and light, which usually gets stuck in as those are forms of energy. We figured they're important because they're the way we communicate with the world around us. They're the way we observe and investigate. And all of modern technology for communication or for investigation in science, understanding how light and sound interact with matter is a very important piece, and how they carry information as well as energy. So we put that as a separate idea because we thought it would both be meaningful to kids to think about it, but also because in thinking about what you want everybody to understand about the world, that's an important one for physical science. The life sciences, nothing surprising there. You have to talk about organisms, you have to talk about ecosystems, you have to talk about heredity and variation before you can talk about evolution, and you have to talk about evolution because it's a key idea of biology. So that was clear. Of course, there's a little bit of politics, and when it comes to states actually deciding they're going to use these standards, and none have yet adopted these standards. So I would guess that within 2 years, 30 states will have adopted. But it's come. So, but one of the places where debate will happen is around the statement of evolution that's there. Also, Science 1, Earth and Space Science, that's what the extra S is. Earth's place in the universe has some cosmology in it, so evolution of the universe. Earth systems, which of course is the main body of Earth science. This is different from what was taught in high school and elementary school Earth science today. It has much more geology and much less of this big picture of system science. It's a field which has evolved, and which as a field stresses this much more today than it did 20 years ago. So this is one of the places where we're asking for a change in what gets taught. And we're asking for a little more at the high school level. Whereas if you look at the physical sciences, what's there is less than a high school chemistry plus a high school physics course, but it's more than the typical 8th or 9th grade physical science course currently runs today. Actually, I think it could be designed really well to do a really good 9th grade physical science course that covered this, and then you could go directly from there to AP level physics or chemistry. And the last one in earth science also is going to get some pushback. Earth and human activity. That is both, this is, one half of that is traditionally taught. And one of the things that gets taught, particularly in elementary schools, is natural hazards. In California it's earthquake, in Florida it's hurricanes. Those kinds of things, obviously we need to understand our interactions with our environment and these very large effects that natural events can have on us. But the other side of the coin, the effects we as humans have on the earth, biologists today talk about we're entering a new era. It's called the Anthropocene. And really, if you ask who moves the most earth, on the surface of the earth today. It's not rivers, it's people. So changing the way we think about what humans are doing to the earth, and climate change is just one of those pieces. But climate change is the piece that's getting the most press since these things came out. Oh, we're going to teach that there's a human role in climate change. Well, we're going to teach that that's something one should be thinking about. So that is another one of the places where the adoption process may become political. We'll see. Finally, the engineering technology. We had engineering design as something you do in the practices. But in order to engage in those practices, there's certain knowledge about how to do it well, which is basic engineering knowledge. Defining constraints, optimizing, working through the design cycle in an iterative fashion. All of those things are stressed in this core knowledge idea on engineering design, how to do design effectively. And then the final one is a very broad one, links between engineering technology and application of science. First of all, that it's a two-way street, that science feeds technology, but technology feeds science. But secondly, that doesn't matter which area of science you're in, there are applications of science which apply to our lives, right? All of technology, and technology here interpreted very broadly, so modern agriculture has its own technologies. Just a pencil is a technology. But how you think, and of course all of medicine, medical science, and how advancing science knowledge changes medical practice. All of those things are buried in this last idea. In the standards, that idea is then threaded throughout the whole set of learning goals. So this is, for each of these, we had 2 or 3 sub-ideas, and we wrote a clear statement of what we think a 12th grade student should know. By the time they finished high school, this is what you should know about this subject. It's general. It doesn't get down into every detail. In order to do some of the things we put in that statement, you're going to have to do some other things to prepare yourself for it. But just the 12th grade level of understanding is what we wrote in the framework. And then we told Achieve, you should take these 3 dimensions and you should write performance expectations for students that weave all 3 dimensions together. So their task was to develop the standards. Standards are a peculiar American thing. It would make much more sense to develop a curriculum. But in the US, we do not have either national or state level curriculum. And so the way we say what students should learn is we divide the knowledge up into all the little bits and pieces that we could possibly test and say, these are the things we'll test. And now you go develop your curriculum so that your students come out being able to pass those tests. And we said, all right, well, let's make what we test not just the students will know, but a performance expectations where the students are expected to actually do something with their knowledge. And you will see when I give you an example of how that looks. These are the 26 states. It's a very interesting mix. It's not red states and blue states, although they're colorful on this map. Kansas, for example, is a state where there's been a lot of fighting over teaching of evolution, but Kansas is solidly on the map, and Kansas will probably adopt. So we're at the stage now where the standards were released last week, and states are beginning to consider them and decide whether to adopt them. California will most likely adopt. You never know what will break loose in political processes, so it's not guaranteed for any one of these states. But my guess is among the first states to adopt will be Wisconsin. That's not on this map. and some other of the states that are not colored blue on this map. It said, we're very interested, but we didn't have the resources to put together a state team and make the commitment to the development process. So where we'll be in 2 years, that's an interesting question, but I'm guessing somewhere around 30 states will have adopted. The process of development was very collaborative. The teams brought in a lot of teachers to help with thinking about what was appropriate at what grade level. They brought in a writing team that actually wrote things and then gave them to teachers to review. Each state had a team which included teachers, it included people from industry, it included some scientists generally. And each state team got about 7 chances to review and give input to the drafts. The teacher professional associations like NSTA and AAPT, American Association of Physics Teachers, for those of you who don't know what that stands for, were invited to review and comment on parts, and really were very helpful in thinking about how's the right way to phrase this for the grade level of the students. There were 2 chances for public input, and yeah, we got somebody from Georgia who said we shouldn't include evolution. It was really odd, actually. He said, evolution can happen within a species, but it can't possibly make new species. That's an opinion, but it isn't scientific opinion. So, and so there was a lot of work done on that. Actually, the last draft came out in end of February, and one of the pushbacks we got from teachers, and there was actually an editorial in a science magazine, saying, if you really want students to engage in these practices, then you've just got too much here. There's just not time. And the number of performance expectations was reduced by about 30% after that last draft to the final one. Although no core idea was dropped, just fewer performance expectations per core idea. Whether that makes any difference or not to the amount that has to be learned, I'm not sure, but it made people feel a lot more comfortable to have fewer. And some of them really were, when you really thought about developing the idea over time, there was a piece in 5th grade that really didn't help develop what came after. Then you can leave that piece out. So there was a lot of work done to try and clean it, fine it down a bit. It's still demanding for students to do all the things in these standards. Will be a lot of work. So I'm going to give you one example. I picked middle school matter and its interactions. I'm going to show you the performance expectations. Then underneath the performance expectations, the standards document has quotes from the framework about what cross-cutting ideas are here, what core ideas are here, what practices are here. And then underneath that, a part which is not yet developed, which they're going to give us, however, there's 2 sets of connections. One is the connection of this core idea to other core ideas at the same grade level or before or after, and the connections to things in the math standards, the ones that 47 states have adopted. So if we're going to ask students to do something with mathematics and science, it should match what we're asking in the math standards. And there was a lot of attention paid to that. And the connections to language arts. Because the Common Core Language Arts standards include a section, starting in 4th grade, they say reading should not just be reading literature. It also should be reading for information. So it's reading in science and reading in history. And so there's connections between that obtaining information in our practices for science and the language arts practice of reading in science. But really, a reading teacher doesn't have the knowledge or the experience to do a good job of teaching a student how to read a science textbook. Science textbooks are not just text. Right? They're diagrams and graphs and equations and charts and all kinds of ways of presenting information. And one of the reading skills is coordinating all those different pieces of information. Furthermore, the way sentence structure works in science is quite a bit different from the way sentence structure works in literature, because science has to express things very precisely. And therefore, we write sentences with multiple subclauses. And if you misinterpret one it or that in that sentence, you don't understand science at all. So how you read science is different from how you read literature. Who cares if you skip over an it or that in reading some literature? In a poem, maybe you have to be that tight, but in most reading of a novel, you don't actually read every word. You read it very quickly if you read every word, and you don't think through those connections so carefully. So it's a different kind of reading skill, and it needs a different kind of support. It's also a development of a language. Right? At the 5th grade, students who read literature at the 5th grade level aren't reading words like analyze and determine and discriminate. All kinds of words which really matter in science that are really science vocabulary. Not just the technical words and the names of things, but the way we talk about ideas. So all of that needs to be part of what science teachers are thinking about too. Okay, so here are the middle school standards. I don't really expect you to read all of them, but we'll just pick one or two and see. So let's pick the first one. Develop models to describe the atomic composition of simple molecules and extended structures. So, and then the stuff in red is what you don't need to do. So that's to help define at what level we're asking these middle school students to model molecules and extended structures. And one of the things we chose to do is put what's inside the atom is in the high school level. And all we're trying to do is get a picture of the particular structure at the atomic and molecular level, and what's the difference between an atom and a molecule and a metal in terms of structure. Or let's go down to the other modeling one, which is develop a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed. That is not something that's well taught in middle school today. But unless you begin to understand materials that way, you don't have the basis for a lot of high school physics and chemistry. So it's very carefully decided what should be here and what shouldn't be here. But also, this is not just know the difference between solids, liquids, and gases. This is be able to present a model that shows how they differ and why they behave in the ways they do. Right? So there's quite a few models here. There's another one that's analyze and interpret data. So the students are presented with some data and they have to do the analyzing. There's another one that's gather and make sense of information, undertake a design project. So you see that the performance expectations each engage in a practice. And they each take that practice and apply it in the context here of particular knowledge about matter and its interactions. And that's the pattern you see all the way through these standards. They're quite different from what most states have had before. And will require quite different methods of testing, methods of assessment to see if students can in fact do these things. Okay, below those statements come these 3 columns. Again, I do not expect you to read it, but these 3 columns are taken directly from the framework document, and they're the pieces of the core ideas. So as you see now, you begin to see the sub-ideas. Under the matter, we had a sub-idea on structure and properties. We had a sub-idea on chemical reactions. Under energy, we had a sub-idea on definitions of energy, and a sub-idea, the engineering one, developing solutions. Right? We have the practices that are being used here, and we have the cross-cutting concepts that come into play, such as patterns. Right? When you're talking about understanding the structure of materials, there's certain patterns to the structure of materials that are different for different kinds of materials. That's the kind of connection to the cross-cutting idea we want to have made. So it's all put together. There's one piece which we didn't, we in the framework said, by engaging in and reflecting on the practices, students will begin to understand and discuss the nature of science. The people who developed the standards decided they needed a little bit more explicit. It's not actually here on this page. Oh, here it is. It's fallen off the bottom of the page here. They added something there about connections to the nature of science, which was not in the framework, but is very much aligned with the way the framework was structured. So this is what comes out, and there's for each core idea at each grade level. So in K5, they made some choices, and not every core idea appears at every grade level. Then they gave middle school as a block, and they gave what should be done in middle school for each core idea. But they didn't talk about what the course sequence is that's going to present those ideas. Then they did the same thing at high school, everything at high school as a block. They later present some possible course sequences, including the traditional ones and some non-traditional ones. One of the issues, as I said earlier, we added quite a bit of earth science at the high school level. So either you divide that up and put it in physics and chemistry classes, which it perfectly well belongs in because it's applying physics and chemistry concepts, or you take it and put it in an earth science course, but then you have a different course structure than traditional. So there's a lot of shuffling still to happen at high school to figure out what's the best curriculum to implement and develop this set of ideas. And I imagine different schools and different states will do different things at this moment with this material. One of the issues is we have a teacher corps out there. It consists of biology teachers, lots of them, chemistry teachers, a few less, and physics teachers, even less. So if we were to say, well, we really need to do physical science in 9th grade, who teaches that? Right? So there's some teacher retraining that needs to be done in order to develop these new courses and think about how best to structure this. We said in writing the framework, and the standards people said in writing the standards, we don't care how you do it, but this is what students need to know. And we need to figure out how students best can learn this. So this is one of the challenges, which means that any new set of standards is not an overnight process. It's not that we adopt them and tomorrow they're happening in the schools. This is still a long path from where we are today, and we're now, right, started in 2010. So we're 3 years into this project of developing the standards and hoping they'll push change in K-12 education. But we know there's still lots to be done, and lots of work on curriculum development, on teacher professional development at all levels, and on helping teachers get the opportunity to experience doing science so they can bring doing science into their classroom, which again is another place where I think university scientists have a role to play. So what's less? Less detailed vocabulary, less disconnected lessons, less rote problem solving, and less teacher lecturing, because you cannot have students engage in all those practices if the teacher's talking all the time. Right? Students have to be talking to one another in the classroom in order to engage in argument and evidence. You can't learn argument by listening to argument. You have to do it. And so the mode of teaching needs to change. And that's very common with these standards and with the math and the language arts. I'll show you that in a moment. More. Discourse and argumentation, student modeling, not just using models that other people give them, but developing and expressing their own models, and more open-ended problem solving, including design tasks. The testing is going to have to be more multidimensional too, which will require different habits of mind, asking students to take their knowledge and apply it in an unfamiliar situation. Something generally today, students tell you that's unfair if you ask them to apply their knowledge in a place they haven't met before. We want them to think that that's fair because that's what you have to do in real life. And so that's what knowledge is good for, and that's what we're going to work towards. So what comes next? State decisions on adoption. Lots of work to develop and test new kinds of assessments. Development of revised curriculum materials. These question marks are because at the moment, nobody's saying, I'm doing that, and there isn't clear path to getting funding to doing that. But it's very likely to come in the next few years, I think, in a variety of ways. And of course, the professional development piece is also huge, both changing how teachers are prepared to become science teachers, thinking about the kinds of science teachers we need to teach this new curriculum. And I do call it a curriculum, even though it's not written as a curriculum. And taking the teachers we have and raising their skills to be able to work in this particular context. All of that needs lots of people engaged. As I said, the standards is the knowledge in pieces. Curriculum has to be designed to get a coherent sequence and to get connections across different disciplinary pieces. That is not well done in the current curriculum, and we're stressing that it's much more important than we've given it its due. So we need to work on it. As I said, implementation is going to take multiple years. Even just bringing this in, I mean, if you haven't been doing this in elementary school, then the students in middle school are not going to come to doing it in the same way that they would if they had 5 years of elementary school of developing models and arguing from evidence. Clearly, with experience, middle school students will be a lot better at this than they are today. So how do we bring it in without locking ourselves into thinking, oh, middle school students can't really do this at the level we're asking them to? Well, they can't today because they haven't had the process of development that will bring them there. So throwing this at middle school tomorrow doesn't make sense. You've got to bring it in and work it up as you go. You can start doing some of it in middle school, but thinking you can go all the way in middle school and high school on the first day you come up with a new standard, after you've adopted the new standards, probably won't work. And most states are thinking of it as a 5-year roll-in process to bring in these new standards. And then, as I said several times already, if teachers have never met the science practices, how can you expect them to be taught or well taught? So this is a summary, just like I gave you for the science. This is the summary for English language arts. And what I want to point to is practice number 3. Conduct valid arguments from evidence and critique the reasoning of others. Right? Now, what counts as evidence in science and language arts is different. But what counts as a good argument is that you present your evidence and your reasoning to defend or refute a claim that either you or somebody else has made. So the structure of argument is not different. The type of evidence is different. Right? Produce clear and coherent writing appropriate to the task. Use English structures to communicate context-specific messages. These are the kinds of things you have to do in science. So there's a real interlocking of the view of education presented in these language arts standards and the view that is presented in our science standards. Likewise for the math, and the central thing, right? So model with mathematics. Reason abstractly and quantitatively. Construct viable arguments and critique the reasoning of others. The overlap is huge. And so what we're really proposing here with these 3 sets of standards is a coherent rethinking of what elementary education looks like, and even what middle school and high school education looks like. And the centering on student argumentation in all 3 of these documents means it's not just the science teachers who are going to be changing the way things look in their classroom, but the language arts and the math teachers too. That's good, because it's really hard to change a culture when you're doing it by yourself and the rest of the school has a different culture. So the culture of classroom argumentation and how you support it is something teachers need to learn. Because there's many teacher moves around getting all students engaged in the argumentation process, ensuring that all voices are heard, developing a culture we have in science, where it's okay if I tell Joel he's wrong, but it's not okay if I tell him he's stupid, right? So there's a whole culture around how you argue, which unfortunately this society has lost. We don't know how to argue in a civil fashion as a society, and we think disagreement means dislike. Well, that's not so in science. And we have to communicate that and support students so that they can do this. This is a very different thing than what they're used to outside of their classroom. So the teacher has to work very hard to develop the culture in the classroom that lets this happen, right? This slide actually comes from a document that's on the website of the Council of Chief State School Officers. That means that's the club or organization of education supervisor, top education person from each state. And this is a document that's helping states decide, okay, one of the big issues in raising standards is what happens to students who are English language learners. Because all of these things have language demands as well as conceptual demands. Can we support students in engaging in these practices and at the same time developing their language ability? I actually think the science classroom is a very wonderful place for language learning to happen, because you're dealing with real stuff, you're engaged in thinking, and that's when you want to talk and when you want to listen and hear what other people are saying. So what we've done here is for each practice, and I'm just demonstrating one, is to say these are the receptive language functions, second row. These are the productive language functions that students have to engage in when they're engaging in developing and talking about their models. And these are the analytical tasks they need to do, because analytical tasks, although they happen in your head and they're not just language, they certainly engage language too. So these are the tasks that you should be seeing students doing, and they're all tasks which facilitate thinking, but also facilitate language development. And anyway, in the science classroom, no student walks into kindergarten speaking science. Right? There's a language development task for every student. So being conscious and thinking about these things, thinking about what the demands are and how you support students in meeting those demands, is something teachers need to do. So this document on CCSO website has such a table for every practice in science, for every practice in language arts, and for every practice in the math standards. And I think it's a very useful way to look at what do we need students to be able to do from a different perspective than the one of what should they know about science. In fact, my daughter is a preschool teacher, and she models it this way. She says, look, what we test is like an unstable thing. Let's take math, language arts. So we test what you can read and what you can write. Phonetics and letters is what she's thinking about with preschool kids. But that doesn't stand up unless it's supported on the one side by language development and supported on the other side by understanding abstract representations. Right? Letters are abstract representations of sounds. Right? Words are abstract representations of ideas. So having development on those things are the buttresses that support the stuff we test. And those things are critical to learning too. There's a third one on the other side which also supports math, and that's analytical thinking. And finally in the middle there's the emotional social development that a child has to go through in order to be able to function at the right grade level in the classroom. So all of those things buttress and are critical to the learning that we value in the classroom, which is the learning to read, learning to write, learning to do math, learning to know science. All of those things are supported by these other skills, which we also have to pay attention to. This is an example from 5th grade classroom, student in a curriculum where students are asked to model. And this is some students' model of air. They were asked, this teacher opens a bottle, and the students raise their hand when they can smell what's in the bottle. And of course, the smell propagates across the room. And then they're asked to explain how that could happen. And they need a model of air to do this. Right? And so here's the student, and he's got, the key says ammonia molecules, movement, that's what the arrows indicate, air molecules. And these arrows go around sharp corners because he thinks that things collide and therefore they change direction. So he's got a pretty good conceptual model of air. This is a 5th grader. Most 5th graders don't have this. You have to have instruction that helps them develop this model before it happens. In the previous iteration, the week before, the students were all putting something between the molecules to hold up the air. Right? So this is part of the process of learning, and good curriculum needs to be developed that does exactly this. And you can see the numbers. The students do pretty well compared to average 5th graders. Once they've gone through a curriculum to ask them to do this, they have a much better idea of what is matter in the gaseous form than a lot of high school students do. So I'll stop there. I can talk about this forever. So here's some fun for you.
First of all, thank you for doing this because obviously it's important, and that leads me to this question. I wonder if you thought about it. So schools and teaching have been around for millennia.
Yes.
Science has been around for centuries. None of the physics you had on your slide was really any newer than at least 100 years old. So why do you have to do this now? In other words, why is it that in 2013 you had to do this? Do you have any thought about that?
Yes. I think teaching is one of those things which has just been, I do it the way I learn it. Right? To a great extent, we teach the way we were taught. So there's a culture which has developed. There is also a research world where people go out and research how brains work and how people learn. And those things are beginning now to come together. And we know there's real evidence from classroom-based research as well as cognitive science research that this kind of learning, by engaging in doing the practices, it's not a completely new idea. I mean, Dewey also knew it, but is more effective learning for a larger proportion of students. So why it isn't what happens in schools today, I can only say that's tradition. And it's very odd. And when you look out there, it's really not fair to say it's not happening. It is, there's nothing in this framework that doesn't happen in some classroom somewhere, right? But it's not coherently happening, and it's not all put together in this way. So I don't think we invented anything here. I think we synthesized the best of what's available into this is the direction we should be moving things. And I also don't expect revolution. I expect evolution. I expect the system to move gradually towards this vision, not to move overnight towards this vision. So I think those two things have to be played out, and I agree, educating parents about this and why we're doing it this way, and why, but I haven't yet met a scientist who looks at the list of science practices and says, that's not what scientists do. Right? So I think that is really a key piece that we need to educate. So we need the voices of scientists saying, yeah, this is really what, and we've done it. We've gone around and researched the Achieve people as they were developing the standards, took their standards and went to lots of university faculty and said, if your entering students knew this and nothing more, would you be happy? And generally the university faculty said, I'd be ecstatic. So I think those voices need to be part of the debate.
Yeah, I had a question related to the issue of the parents. And so how do you feel about the concept of homework? I mean, should kids be sent tons of homework? That seems to be the tendency these days. Or should most of the work just happen in the schools?
What the kids should be doing in the classroom and what they should be doing at home are different from the way they are today. So generally today, particularly in elementary school, homework is rote, boring punishment. My daughter has a 6-year-old and an 8-year-old, and my daughter hates homework because she's the one who has to work hard to make sure her kids do the homework, right? And it's not very useful work for the kids. There are some, there is value to practice for certain kinds of skills, and there is value to asking kids to become independent learners. Most homework doesn't do that, but it should, right? So in high school, homework should be asking students to do the part of this that can happen outside the classroom, right? And then bring it back and talk about it in the classroom. It's a different balance. It's not going home and doing rote chores on a form. Sometimes, yes, it's going home and practicing a certain kind of problem solving, or practicing a certain. So the problem in education, right, is we always develop these false dichotomies: rote problem solving, procedural, versus applying knowledge in new contexts. Well, we need both, right? As you work in a field, if you don't become a rote problem solver at the trivial parts of it, you're not going to get very far with the more advanced parts of it. So how do you get that practice part as well as that thinking part? That has to be balanced. There's a lot of talk these days about flipped classrooms, where the doing the problems happens in the classroom with discussion, and what the kids do at home is watch videos of Khan Academy or something like that to learn the math concept instead of hearing the teacher lecture. They hear the Khan lecture, which is more palatable because it's divided up into 10-minute segments and they can review it. So there are ways of doing this differently, and we're trying. One of the things we talked about a lot as we developed the framework was we've got to not develop a bridge too far. We can't go so far that the system can't respond and get there, but we want to push the system to respond in fairly strong ways. It remains to be seen whether we hit it right, but at least there's a lot. If we talk to like the science teachers at NSTA last week, they were really enthusiastic about what's here and about the options it gave them for the kind of teaching they would like to do. So there is a community out there for whom this is natural, and there's a community out there that will resist it. And the proportions are always a little bit big. And there's a community that can be brought along that won't resist but isn't ready to do it tomorrow. So all of that there's just a lot of work still to be done.
So you've talked to FAIR mentioned a few times scientific literacy and reading, but most of the scientific texts I read as a middle schooler confused. Either just terrible rote memorization textbooks, or there was something that was completely contrived and trivial. So where are you going to actually get the materials?
So there's no reason why students shouldn't be reading magazine articles. Things other than those terrible textbooks, and we need new textbooks desperately. I have a student at Stanford who was actually studying the linguistics of science textbooks at middle school level, and he brought the textbooks to me to say, which sections should I analyze? And a middle school, a 6th grade earth science textbook, I opened it to 6 pages, and I found 6 things that were just like wrong. So, it's not just the language in it that's terrible, it's the science in it is terrible. So we need a better system for producing, reviewing, and developing resource materials, curriculum materials. There are some good stuff out there, but there's also a lot of really second-rate stuff. And one of the sad things is that the system within the schools that chooses what to use can be very fooled by a good-looking book, which is not a good book.
So how do you move from an assessment that looks like this, you know, that's very, it's somewhat open-ended, and so how do you move from this to a more like standardized state testing?
No, you move the state testing to this.
Okay. Do you expect a lot of resistance in that, because it seems like...
So there's actually another academy study going on right now that I'm serving on, which is about what should assessments look. If this is what science education should look like, what should assessments look like? It's a struggle. It's going to take time. There's technology helps, right? Having students, for example, simulations where students can manipulate the variables and then interpret what happens. You can do very interesting open-ended tasks for students. And it can collect a lot of data on what they're thinking just by what, you can watch every keystroke they make, right? So the ability to measure is way beyond the ability that's used with pencil and paper and multiple choice questions, right? But even this is a pencil and paper task. It's a much richer pencil and paper task than asking them, you know, air is made of, and give them 3 multiple choice questions or 5 choices as to what it might be, right? This is very, very different. And this is what we need. That's why I put that example up. That's a test question.
You need a human to read it though. That's
maybe,
maybe.
Or maybe you can develop technical ways of doing it. It takes resources to do the development work, and that's where we're short at the moment.
So how interconnected are the different states' curricula? Like if Kansas decides they don't want to teach evolution, does that affect California?
Well, up until now, it had no effect at all. If Kansas and California both adopt the same standards, then they're both going to be teaching evolution. Right? Now, it turns out that even in states where evolution is in the textbook, some teachers in some areas just say, well, I don't actually teach that section, because I get too much pushback from the parents. Right? So, how much control you have remotely over what goes on in the classroom, that's very limited. But at least it's in the textbook.
If it's part of the assessment.
If it's going to be assessed, then and some teachers will say, I'm teaching this not because you should believe it, but because you're going to be tested on it.
I have a question of my own. How prepared is the core of teachers for these standards? I mean, how long is it going to take?
Well, it's very variable, and it depends on what level you're asking at. Unfortunately, one of the impacts of No Child Left Behind, which is a very big stress on scores of students in math and language arts, is that science in elementary school, and particularly in early elementary school, has all but disappeared. Right? 1 hour a week of anything other than reading and math. And the kids who are behind in reading and math get pulled out of that 1 hour a week to get some extra reading and math. So the recent entry into teaching, teachers haven't much experience in teaching science. And certainly not in teaching science this way. So at the and also, you know, most people don't go into elementary school teaching because they love science. They go into it because they love kids, and some of them love science. So having a sufficient resource of elementary teachers in every school who can support the other teachers to do this kind of science teaching, and having professional development for elementary teachers, that's a big, big job. Middle school and high school, I would say it's roughly third. Right? There's a third of teachers who would love to be doing this. They won't get it all right, but they're ready to jump in this direction tomorrow. Right? There's a third of teachers who, no matter how much professional development you do, they don't want to do this and they're going to resist. And there's a group in the middle who are pretty neutral about it, but can be moved into doing it, but it takes more professional development. So it's a really big challenge. to bring the teaching profession to where it needs to be to make this happen really effectively in every classroom. And unfortunately, and this is another issue for society, not for science teaching, the resource of good teachers in poor schools, and I mean not poor academically, but poor socially, socioeconomically, is poor. We have, those districts tend to pay less, and so what happens is new teachers move through those districts and into better paying districts where they have less problem with all kinds of bureaucratic difficulties that those districts tend to have. And so the chance that you'll get a qualified, say, high school physics teacher is much greater if you're in a suburban district than if you're in an urban or a rural one. So the unequal distribution of teaching resources is part of the problem we have to look at.
I have so many. This was totally a pleasure to listen to. I have so many thoughts and ideas. But my question and my comment is that I think that this audience may not be your most natural audience for this, but I think it's an important audience. Because in California, at least, what happens in the high schools is strongly driven by what UC accepts as its
right, and that's actually a good point. It's something I didn't mention, and it's something we need to work on. For example, today, even if there is a high school earth science, it does not count under 8F requirements because it's not a, quote, lab science, even if it has field experience in it. So that's really stupid, right? The modifying what the UC system accepts as good high school science has to go along with modifying high school science. So one of those fronts that still needs to be worked on, and it's true in most states, in many states, that it's the university system in the state. So there's two things. One is the high school graduation requirements. In California, that's 2 years of science. There's no way you can cover the high school standards here in 2 years of science in high school. So we need 3 years of science in high school in California. Just last year, Jerry Brown went in to move it to 1 because he saved money, right? Lab science is expensive compared to other classes in high school. So there's that, graduation requirements, and then there's UC entry requirements. Those are the two things that really define what goes on in high school. And if we want to change high school, both of those things have to